Yes. Well, I'm going to have to work with the microphone to get the... I think it would help if I turn the microphone on. Okay, so, can you hear me now? Huh?
Sounds better.
Well, it's showing me that the sound is better, so.
I can hear something.
Okay, thank you, Casey, for your feedback. You know, it's a huge insult to be an engineering professor. Like, hey, I can build robots, and hey, I can't figure out how to turn on a power switch. Dang it. So yeah, I struggle at the basic things in life. But you know this by now, so it doesn't make me a worse engineer. It just makes me a bad person. Anyways, so what we talked about last time was I gave you an introduction to the course. Whole purpose of that discussion was kind of just a 20,000 foot view of what is control systems. Also, I got to talk about punching Sam Vanderslice in the face, which I'm still scared. I've had some nightmares lately. I'm in therapy, but no, Sam's a good guy. But what I wanted to talk about today is I want to give a little bit more in depth as far as what a control system really is. Okay, I want to give you a really solid understanding. Some of the examples I gave you last time for what a control system is: a helmet. Helmets take some input, some force input, some impact input, and convert that into an actual, well, force on the head. But it's not a high pressure, low area force. It's a distributed force that happens over a significant amount of time to reduce that impulse and really make the impact a lot safer. We talked about vehicle suspensions. Every vehicle suspension is a control system. As you travel along the roadway with, I'm going to draw a really poor car with only one wheel. As you travel along the roadway in this direction, your car is not going to experience a perfectly flat, is this even visible? It kind of is. Well, I need to turn on this light. Or this light. Nope, that is not the right light.
Oh yeah, that's not. Let me turn off these lights.
Oh yeah, mood lighting, yeah.
Oh yeah. The brightness on your camera.
That looks worse. Let's go back. Although I do like the mood lighting. But let's see if that is any better. No. Oh well. I think I'm just going to have to use a black marker next time. Were you guys able to see any of what I was writing on the board?
Yeah.
Okay, maybe it's just that my screen brightness is down. Okay. Anyways, as your vehicle travels forward, your vehicle doesn't encounter a perfectly flat roadway. Certainly not if you're me driving to work and going through 50,000 construction zones. Have you been to Lincoln recently?
Yeah. Right.
Everything sucks. Everything. Good. Yeah, it's like, well, let's see, we're working on Highway 77. Let's do construction on every other road too. Like, no. What happens when your vehicle travels forward is the roadway is never flat. It appears flat for most of us. Road designers do a good job of trying to make it flat, but really what you have is even a roadway that has a slant like this that adjusts back, that's still a bump. And with as high of a speed as your vehicle is approaching that, your suspension is going to have to counter this. Otherwise, you're going to feel like you're jostling up and down, or really badly. Anybody has off-road tires, you really feel the vibrations of the roadway really well. I drive a car that's meant for comfort, so I don't feel a lot of the vibrations. But my brother bought a RAV4 this summer, and of course I drove it, and you really feel the roadway. With a lot of older trucks, where the suspension is kind of getting shot, you don't feel it as much, but they bounce a lot more. It's another issue of how is it going to handle this kind of a bump. If it handles this kind of a bump by bouncing, what happens is your wheel compresses and your vehicle doesn't move. And then this force then causes the vehicle to get launched a little bit. And you get a bounce from that compression. That's actually an underdamped system. Oh yes, I'm using those painful words that I talked about in the lecture last time that we're going to be seeing resurface this semester. We're going to be talking about second order differential systems again. And a suspension system has a damper and a spring, and the vehicle is a mass. Spring, damper, mass is a second order system. It's an equivalent to a capacitor, an inductor, and a resistor, where the resistor is the damper, the capacitor is the spring, and the inductor is the weighted mass. So, but we'll be talking about that. Turns out the math behind dynamic systems like this is identical to the math that goes behind electrical systems, which is also identical to the math that goes behind hydraulic systems, pneumatic systems, and rotational systems, and heat transfer systems.
Why?
The reason why that is because they're all linked by the fact that each one of them has a power formula. Each one of them has an energy formula, power being the derivative of energy. So the fact that you have these two components that play on power, force and velocity, torque and angular velocity, current and voltage, all of these components, they all play into why the math is still the same, because we have the same calculus that we use to derive one equation that we can use to identify all of them. And yes, some of those equations are deliberate. The reason why we deal in voltage and current in those types of systems is not just because somebody thought, hey, we need to stop talking about charges. It's because it has to do with power. Okay, so anyways. So this is, you have a suspension system that is a control system. You have actual control systems in your air conditioner. I mean, control systems are everywhere. You will have a hard time finding anything that isn't a control system. Quite frankly, even a light switch is a control system. A fuse box. You want to talk about voltage regulators that are used by power plants. Those are massive and incredible control systems that are used to ensure that when we plug something into the outlet, we get 110 to 120 volts, not 110 to 280 volts, which would fry just about anything. Our systems aren't meant to be able to handle that. So all of this, I mean, all of these are linked by the fact that they have control systems. And we could sit down and make this list so big it would cover all the whiteboards in this room. I don't want to do that. Because quite frankly, the fact that we started writing helmet is your first indicator. Your cell phone has millions of little control systems in it. They control screen brightness, control to make sure that when you touch a button, that it doesn't like, okay, I held my finger on the space bar for 0.5 seconds instead of for 0.2 seconds. So there's now 20 spaces. No, it doesn't do that. There's a control system integrated into it that dictates, okay, if you touch it and you don't hold it, then it doesn't want multiple spaces. It's just, that is a control system in itself. Phones are great examples of control systems. I talked about last class how a lot of the beauty of what Tesla has done has been to integrate control systems, your lane assist, those kinds of things. Control systems, they are a huge area of improvement in being able to design a better control system. By the way, nobody has designed the perfect helmet. Nobody. There are still people who are designing helmets right now. And we have the most advanced technology we've ever had in history. But we still can't figure out a helmet design. And we've been playing football for 150 years as a country. We still can't figure out a better helmet design. This is a multi-billion-dollar industry. And we still can't figure out a better helmet design because it's a control system. And because control systems, quite frankly, are really difficult. Yes. So what is a control system? If I were to just give you this list and say all of these have control systems in there, what do you think a control system is? I'm asking you people in the room. Have I given you any kind of indicator of what it might be yet? Or have I only made it more confusing? You're free to tell me I've only made it more confusing. You guys are giving me dull stares.
I'm on my thinking face right now, so you can't really see.
Oh, right, the mask. Gotcha. Okay. I can only see the eyes. What is a control system?
Is it kind of like a function in Python where it serves its own purpose and it has like the introduction that like kind of pulls in all of your the libraries, right? And then you have the set of the function that runs the libraries, and then you have
Okay, that was one of the best descriptions of the control system I've ever heard. Nice work. Because that's exactly what a control system is. In order to understand a control system, you have to understand two words. Input and output. Okay? And your function description, there you go. Didn't even know that that's where I was headed. But this is where I'm headed. Every function has an input, every function has an output. Okay? What a control system is it does act as a function. It takes the input, it does something with it, and it outputs something. That's all it is. Okay? A helmet takes the input of a very fast impact, and it outputs a slow, steady, distributed load impact. Vehicle suspension, it takes very high vibrations, and it averages them out, and it produces nothing, ideally, in a good suspension system. Or it takes a very long, steady, continuous input, such as the tire being compressed by traveling up an incline, and rather than doing nothing, which would cause the front of your vehicle to eventually hit that incline, which you don't want, what it does is it gradually says, okay, adjust the vehicle angle, adjust the vehicle height, so that it doesn't run into the incline, but actually matches the slope. Your vehicle is very heavy, and trying to get this and then force it to rotate, that's a control system. That's the output. Vehicle rotation. Okay? Air conditioner. The input is the ambient air temperature, ambient air humidity. The output, cool air. It's also a humidity, and it's also an ambient air temperature, but it's different because it's conditioned. Light switch. The input is, well, what do you want? Do you want the lights to be on or off? Okay, here I only want the light to be on a little bit because I like me some dark mood lighting. The output is the light intensity. Input is, quite frankly, just a little switch. Inputs and outputs are integral to understanding control systems because each one of these has something that's coming in. And they're always going to be some physical characteristic, okay? Inputs and outputs. Well, let me go ahead and define these. An input, what an input is it is any physical property and here's where I'm going to detail out what a physical property is. We're talking force, torque, speed. I think I'm displacement. Acceleration. Momentum. Weight, which is just another force. Voltage, current. Heat, temperature. Pressure. Volume. Yeah, okay. So this list is gigantic, and I'm not done. It's anything that you can really write. Any of the units that you used in physics class are fair game. Not only that, etc. I mean, you could even have the intensity of nuclear radiation. That can be an input to a control system. And it is at a nuclear power plant. Okay? Or, so not just physical property, but it can actually be physical information. Like I can say yes, and that's an input. Okay? So it is any physical property or information that is pertinent to the function or desired behavior of a system. Okay? So an input could be anything. But the key condition here is that it has to be pertinent to the function or desired behavior of a system. Okay? When we talk about helmets, if the temperature of the helmet doesn't matter for the force transmission, yes, it can be an input, but it's never going to get used. If the amount of radiation, nuclear radiation going into that helmet, if that's not pertinent to what the behavior is, that force transmission, yes, it can be an input, but it's not going to be used. Going back to Drake's good analogy, which I am still just really floored by that.
I took CST over the summer, so it's still kind of fresh.
I'm just saying, man, dang. You can input that into the function, but that variable doesn't do anything. Okay, there's no reason to have that variable in the function if it doesn't have any real purpose. So an input is an input to the function. It is something that is used to obtain the desired outcome, okay? And I also state information because you also personally have to indicate what you want that desired outcome to be in the function. As the person who designs the system code, sometimes you require direct feedback. You require a user to push an enter button and say, yes, I want that. Okay? Yes, I personally would like to have a lighter screen. I have the ability to adjust my screen brightness on my computer because even though it has control systems that can indicate the brightness of the room, maybe I have difficulty reading dark screens no matter what. And I need this to be so blinding that my irises are burning. Okay? Maybe that's what I need. I have to have the ability to adjust that. Because if it's going to operate the way I want it to, I have to be able to give it that input. And that serves as a form of direct information. It's basically like an override. Okay? An output is the same thing, just a little bit different. The output is the behavior of the system. And when I say behavior, what I mean is any physical property that is being enacted by the system and any information that's being output by the system. Okay, now what this means, and I'm going to go back and I'm going to define control systems now using this, which is going to sound a whole lot like what you already said, so thank you for bearing with me and having some patience here. You've already got this class. I think you just earned an A. What a control system is any system that takes inputs, performs some procedure on them, and modifies that inputs to have controlled outputs. And here I'm going to go ahead and say any system again. A roadway can be considered a control system because it does take vehicle vibrations and it does mitigate them. A lot of the surfaces that we do, the buildings that we live in, have control systems built into them. Okay? This building doesn't vibrate when I walk down the hallway, hopefully. Why? Because it has the control systems that mitigate that vibration. And instead of turning it into, okay, everybody gets to feel the vibration of me walking. Well, yesterday I did push on this whiteboard and I made the entire roof creak. That was bad. Wait, no, that was 2 classes ago. Yeah, that was in this class. Everybody that is currently online, go see that. Yeah. Okay. Takes inputs, modifies them, or controls them, or reads them, adjusts them, whatever, and use them to modify the behavior of the system. And here again, I use the word behavior. Behavior is the output. Okay? System. It takes inputs, modifies them, and uses that to adjust behavior. Okay? What that means is there is no control system if I walk over here and I lean on the board like this. There's absolutely no control system. The board is feeling the direct pressure of my hand. Okay? If I were to implement a control system could be as much as simply taking this roll of paper towels and putting that between my hand and the board. Because now the input, being the force of my hand, is now distributed across the entirety of the paper towels. That becomes a control system. That's it. Okay, is that the stupidest device ever? Yes. But that's how a control system can be as simple as flipping on a switch, as simple as putting a roll of paper towels between my hand and a board, or as complex as the massive amount of circuitry and neural networks involved in controlling power supply. But they all run off of the same principles. They all have some inputs, some outputs. Okay? In the larger system, what makes it a more complicated system is that it has more inputs. The complexity of the system, having more inputs, being able to read power usage by each individual house. I mean, that is a massive amount of inputs, and that varies constantly. There's no defined function for it. They have average functions, which are basically, here's what the expected power usage is of this area based on the temperature outside, based on this. Those are control systems, and yeah, that is used to dictate how much power is being output. But at the end of the day, the more inputs that it has is the reason why it has to be so complex. Okay? Having one input, which is the force of my hand on the board, makes this system really, really simple to analyze. Okay? Vehicle suspensions, where vehicle suspensions only deal with force and displacement, make them fairly easy to analyze. Now, again, it's a second order differential system, so you got to do some sick calculus in order to figure it out, but it is calculable. Okay? Does this definition of a control system make sense? Okay? I will probably continue to use your definition because I really like that. It's probably one of the best definitions I've heard. So, let me check. I'm supposed to talk about something else. No, I don't think I was. I think that's everything I had for the online class. I'm going to go ahead and shut you off. I'll see you Tuesday. Please like and subscribe, and submit to my Patreon. Every donation helps me put high quality content.
Thinking about making an OnlyFans.
No.